Okay, so ugh, terrible.
I'm so sore.
Oh,
We did like these squat thingies.
Yeah.
They were not fun.
I don't know if that was my best drawing there, but I think it looks a little bit more like this. Okay, so what will the reflection look like? I'm not gonna be like super picky, but I mean, if it's definitely, if it's clearly not in the right spot, I'm not gonna give you credit. So how would I reflect this? Well, just look at each point and reflect it over the line. So starting with F up here, if F is right there, where would its reflected point be?
Oh, wait.
Okay, you kind of figure out how far is it away from the line. If I go straight towards the line, like at a perpendicular angle, however long that is, it should be matched on the other side. So F prime is right here. So it's a little bit harder without the graph paper stuff, but it should be the same distance away from the line, like on a perpendicular line to the line you're reflecting over. Where would the reflection of D be? Well, D is pretty close to the line, so its reflected point would be pretty close. And then E is pretty close to the line too, so E prime. It should look symmetrical. Mine doesn't look perfect, but it's pretty close. Kind of like wings.
So on 2 it says find the line over. Oh wait, never mind. I got you.
Yeah, 2 is the same. Oh no, 2 is different, isn't it? So on 2, you just draw the 2 lines that they drew, and then you're supposed to draw the line of reflection, which would just be splitting right down the middle. Number 3, graph paper. Forgot about that. All right, number 3, graph each polygon with the given vertices, then reflect in the given line, state the coordinates of the image's vertices. You know what, I'm not gonna make you state the coordinates on this one, so I'll just look at the pictures, fine. Okay, here we go. Okay, we're supposed to reflect over the x-axis. Which one is the x-axis? This one, yeah. So, D over here, looks like a P, is 1 above the x-axis, so its reflected point, D prime, is going to be 1 below. A is 3 below the x-axis, so its reflected points will be 3 above. C is 4 above, so 1, 2, 3, 4. B is 2 up, so B prime will be 2 down.
Mr. Brown?
Yeah.
Wouldn't A be on 2 negative 3, 'cause we have it on 1 negative side.
Oh yeah, I did, didn't I? Okay, let's just do this. There we go. Alright. Where was C at? Didn't get the dot. Doesn't look really much like wings this time, but it is symmetrical over the x-axis. So. Number 5, write a mapping rule for the reflection in the line y equals x. What happens to the coordinates when you reflect over y equals x? That's what they're asking for.
Like staircase or something?
No?
Oh,
You guys remember what the line y equals x looked like?
straight line.
No, it was vertical line. What happened when we reflected over the line y equals x? The x and y values switched places. So here's what they wrote. Point xy turns into point yx. So this is what they're looking for. Okay, on 6, we did do one of these, but it's been like 2 or been a long time ago. What do you think the V with the little arrow symbol, 2, 3, what do you think all that means? You guys remember that at all? Okay, it's a vector, which is just like it's represented by an arrow that tells you like what direction and how far to go and all that stuff. But 2, 3 basically means we're supposed to move the graph right 2, like 2 in the x direction, and up 3 in the y direction. So on 6, you're supposed to do a translation, just move everything right 2 and up 3. Got it?
Yep.
All right, number 7, JKL translated by vector -2, -8. Okay, we don't have to draw number 7. We're just asking where the points would go. So J is at 5, 8. So if the vector that describes the movement is -2, -8, how could I find J prime? Okay, what's this vector gonna do?
Left 2 down.
Right, the x value is gonna drop 2, the y value drops 8. So all we have to do is, guess what? Subtract 2, subtract 8. So it's just gonna be 3, 0. And then you do that with all the coordinates. K is at 2, 6. So if I subtract 2, I get 0, and 6 minus 8 is -2.
-6.
Was it a -6? Yeah, it was. Okay, so that'd be a -14. 2 and subtract 8. L prime is -6, -5.
Does the shape on it matter? Like if it's a triangle or quadrilateral? Or do you still just do the exact same thing?
What are you talking about?
On number 7 and 8, it says JKL is a triangle, but on 8 it's a quadrilateral. That doesn't matter.
The question they're asking is where would the points be? So these are the answers. We're not even drawing it. So.
I know that, but I was just didn't know if it changed the answer.
No. Oh, it would be the same shape when you
Yeah,
drew it.
we got it.
Okay, 9 is kind of the same thing, but they didn't put any numbers in there. Weird, right? So the vector this time is mn. So that means we're going to move up or to the right m. The x value is going up by m. The y value is going to go up by n. So the first point, f, a, b, okay, where is f prime going to be?
A-M-B-N?
AM means a times m.
Oh, A minus M.
No,
A plus M.
a plus m. We're going up by that much. Now if m was negative, it would be like a minus m, but yeah, we just add the values. F prime would be at a plus m and
B plus
n, right, n plus b, b plus n. And there's also a g. There's only 2 points.
It's a line.
Okay, g is at c. So g prime, same thing, just c plus m, d plus m, n. On 10, remember you're going from L to L prime, H to H prime. So you're starting on the black one, ending on the red one. So you just got to describe the translation. How's it moving from there to there? 11, state the translation vector if you're going from 6, 2 to 10, negative 1. Okay, okay, if P is sliding from 6, 2 to 10, negative 1, how far is it moving in the x direction? How do you get from 6 to 10?
Plus
Positive 4. On the y value, how do you get from 2 to negative 1?
here's 3.
It's going down 3, so it's minus 3. So I just put 4, negative 3 is the vector. Like right 4 down 3 is usually what we said, but. Oops. Next one is 27. Rotations are pretty hard to do without the graph paper, so I thought, we'll skip that. We did some rotations yesterday, so. Even on the graph paper, we get them wrong sometimes. So 27 is going all the way over to the third page. Identify each illustrated transformation and state whether or not the transformation is an isometry. You guys remember what isometry meant?
With 180.
It means it keeps its size. So everything we did this chapter besides the dilations was an isometry. So we did translations, rotations, reflections, and even that one day we did what they called a glide reflection, where you slid it and reflected it. I don't think they really needed to add because that's just a combination of a translation and a reflection, but it's okay. So on 27A, how is that little 6 thing, how's it moving from the black to the red? What's happening there?
Flexes.
How do you get it from there to there? What did they do? They reflected, they translated, did they rotate it?
Black.
Yeah, I just slid it over. That's a translation.
So what the difference in the flex?
Like where you flip it over a line. Okay, is a translation an isometry? Yeah, keeps the same size. Okay, B. That is not a translation, right? How can you get from that to that? No. I rotated. Actually, it's 2 things. That's why it doesn't work. This is not the right picture. I don't know if I can draw it right. Let me draw it like they drew it. Like digital. Digital 6. No, that's the wrong way. There we go. It's like a 9 now. No, I was right the first time. I was looking to draw one. Okay, well, is it a rotation? No, if we rotate it, it does not look the same. Is it a slide? No. It's not a reflection, because if I just reflect it from here, it's really 2 things are happening.
Slide.
Right, they slid it over here. Whoops, forgot I had rotated it. They slid it over here, and then they flopped it down like that. So yeah, we'll call that a glide reflection. So it's a translation and a reflection together, but glide reflection. Is it an isometry? Yeah. Only the dilations were not isometries. Okay, C goes from a 6 to a 9. How does that happen? Yeah. If you rotate the 6 180 degrees, it looks like everything. So it is a rotation. Is it an isometry? Yeah, keeps the same. Isometry just keeps the same size. Looks the same. Nothing warps or anything. What's D a picture of?
It's just shrinking.
Dilation. Shrinking is a dilation. Shrinking or expanding is dilation. And that is not an isometry now. Uh, 28, what's a translation followed by a reflection called? We just mentioned it like a minute ago.
Glide.
Glide reflection. Okay, 29 is weird too, but whatever. If you do a 125 degree rotation around a point and then do 235 degree rotation around the same point, what's going to happen?
We'll make a full circle.
So what happens when you rotate something 360 degrees?
Stays the same.
It's the same. So what the book called it, and I don't really care if you remember this part, I do kind of, you do need to know that 360 just makes it go back to itself. But the book called it identity, which just means it's itself. That's what it means. which has neither line symmetry nor rotation. So we're looking at pictures A, B, C, and D. It's like matching. Which of those 4 pictures does not have line symmetry or rotational symmetry?
C. B. Oh, C, yeah, C.
Yeah, if you draw right down the middle of the house, the two side, left and right side of the house don't look the same. So it does not have line symmetry. And if you rotate it, it doesn't look the same until you get back to the original, to 360 degrees. So yeah, you are correct. 30C does not have any kind of symmetry. Okay, 33. Do you guys remember point symmetry? I mentioned this one yesterday, but it wasn't one of the questions yesterday. Point symmetry is 180 degree rotational symmetry. So like a rectangle has point symmetry. If you rotate it 180, looks the same. So
D.
which of those does have point symmetry? D, yeah, the rectangle D. Tomato. Objects occurring in nature often exhibit, if not, in general, if not perfect symmetries. Describe the general symmetries in these photos by stating the number of lines of symmetry. Magnitude and order, you guys remember that from yesterday? The magnitude is how many degrees you turn it before it looks the same. And the order is how many times you can do that before you get back to the start. So anyway, on 35, that little flower looking deal, how many lines of symmetry could we draw?
2.
Don't make me draw this on the board.
No, wait.
We got a 2 and a 6. Any other opinions?
Wait, maybe 4.
The top one is like bigger than the left and right ones, right?
Yeah.
Just pretend this looks right. This is the general idea. So that definitely works. That definitely works. So there's 2. Does this work? No. If we fold it this way, this little petal doesn't match the big petal. So no, it's just the 2. So anyway, first answer is 2. Second answer, what's the magnitude of the rotational symmetry? So how many degrees do we turn this thing before it looks like it did? Right. 90 degrees doesn't work because this petal is not as big as that petal. So you have to go full 180 degrees. So what would the order be in that case?
2.
2. You turn it twice before it gets back to the start. And then, does it have point symmetry?
Yes.
Yeah, point symmetry is 180 degrees rotational symmetry. If you turn it upside down, does it look the same? Yes. On that tomato, is the top of the tomato and the bottom of the tomato identical? No.
But
It does have a line symmetry, but
it does.
yeah, the left and the right side of the tomato are the
So
same.
the seeds are equal.
Okay, it's not like completely perfect. It's just in general.
Well,